No, no, we will, what happens is that we will check both. The less number here will mean that that failure may occur before the other one. So let me say that if I check and the number I have here, the number I have from tear out is less than the number I have from bearing, the tear out may occur before bearing. And the strength of your connection at that point becomes this tear out number instead of bearing. On the other hand, if I check and this bearing number is lower than tear out, the bearing failure may occur before the tear out. And this becomes the strength of that bolt hole at that particular point. So it's either one of them. I can say, okay. Too small. I can say minimum 2.4 FU dt or 1.2 FU LCT. You choose the minimum. Okay. I don't know why they do this in the spec. They just give you two formulas and then use the equal or greater operation, which is very confusing. Basically, just the smaller number between the two, right? Simple as that. Okay, so it's just part of the tension members, because if there's no hole in tension members, you don't have any job to do, just check the yielding, right? But if you have holes, you have a little more to do before you can say how much your member can carry the force. Okay, and still enjoy drawing. We should go back to the slide maybe. Okay. Okay. Think ready to move on. So let's come back here. So this slide will give you the summary of things that when you have the tension member with holes, this is what we need to do. Okay, and it can yield the one anywhere, and say cross section 1, anywhere of the member, and it can rupture, and rupture should always occur at the first line of the hole, right? It's not going to occur at the second line or the third line. If you want to know why, you need to draw a little thing that we call free body diagram of the member, and you will know. Okay. And then you can have block shear at number 3, section number 3, or bearing tail at each bolt hole number 4. So that sums up the tension members. Okay? Or if there's a hole, you can either have the yielding or rupture plus shear lag if you don't connect all. If you connect all, you don't need to check the rupture because it will never happen before the yielding. But again, it's highly unlikely, if you ask me. Okay. That's it for tension members. You know what? I found my first mistake because I just updated the slide and it's always something like this. My apologies. Because we're now going to move into the compression member, but on top it says tension. I'm sorry. It's just a mistake. Copy and paste. Oops, caught on video as well. All right. So are we ready to move on to the compression member? For tension, it's pretty, say, comfortable and convenient because we know that if we apply tension to the member, it's either going to reach the yield point or the ultimate point. But for compression, we don't know when the failure is going to occur. And whenever it occurs, the stress at that particular point we call the critical buckling stress. And that is what FCR stands for. Okay? That means when we consider the design strength of the compression member, which is not this one, okay, we're gonna need to check the buckling of the entire member. And we also need to make sure that each element in the cross section does not buckle as well. Because we have this because you think about the steel. Now, yesterday I was in a conference held by SSI, and some say steel is lighter than concrete. That's not true. If we talk about specific gravity, steel is much heavier. But in terms of material, when you consider the strength of the material, steel is much stronger than concrete. And that is why we are not going to use the column made of the steel entirely, right? Because it's going to be heavy and inefficient. This is the main reason why we use the shapes such as H, I, C, because we utilize the strength. We don't need a lot of weight, because that much will be sufficient. And because we start utilizing the shape and edge, for example, so the problem with utilizing the shape is that if you create the flange to be too thin or the web to be too slender, it may have its local failure. So the flange may fail, the web may fail before the member fails. So that is the idea of local buckling. I don't want to touch the specific words, because you may think, what is this? I don't get it. So it's gonna fail, and the failure we call it buckling. That's all. So if the flange is too slender and it may fail before, or the web is too slender and it may fail before, that will be another issue that will prevent us from reaching F critical. Because F critical is when the entire member buckles or fails, right? But if your flange or your web or whatever element you have in your cross section is too slender, that failure will occur before we can reach F critical. Okay? And so if we have a very solid section, the flange is thick, the web is strong, we will reach F critical without problem. But if they are not like that, they're too slender, we may not reach F critical. Something bad will happen before we get there. Okay, so that's why we need to consider these two possible failures under compression. And the general idea is this equation, ladies and gentlemen. No matter what you do, no matter what I talk about, it all comes down to this equation in the end. The stress at which failure occurs multiplied by the area. And now it is our job to find the appropriate way to approximate that stress. Okay? And once the calculation here is done, again we get nominal strength, the calculated strength. You can turn this into the design strength by multiplying the phi if you use LFD, or divided by the factor of safety if you use ASD. Okay? So that is the general idea. What time do we have here? 5 minutes to 11:30. Now do you know that guy? Euler. Leonhard Euler, the best mathematician the world has ever known. He is he was, right? Because he passed a long time ago. He was the only person on earth that had two numbers named after him. One is the E, 2.71, that's Euler number. I don't even know what it is for, but it's just some magic number that once you take the limit, everything will go towards that 2.71 thingy, whatever that is. Anyway, would you rather have some number, called after your name? It would feel kind of strange, right? That's a peanut number, like 0, because you get a lot of zeros in the exam. So 0 is a peanut number, something like that. That would be not sounds very nice. Anyway, so Euler was a genius. He had done so many things in his free time, including this Euler buckling law. So the question is, long time ago, when people start questioning the things that I mentioned earlier, you apply compression to member. What is the load that caused buckling? How can you come up with the mathematics to explain that? It was crazy enough. And they did anyway, by using a little mathematics called differential equation. Can you believe that? Because they come up with the equilibrium equation that contains the first and the second derivative. So the only way to solve the equation with two derivatives is just using the differential equation. And they obtain the solution. And you can tell right away, because there is pi in the solution, that this is from differential equation. It's some kind of trigonometry function. Yes. So let's not go into that. But that means, can you believe that? This is the exact solution, solved by using mathematics. Wow. That's why Euler was a genius. But when you plot this, Euler discovered that the strength of the member under compression is a function of the thing we know as the slenderness ratio, or L over R. R here is not the radius of gyration, or it is. It's not the radius of the fillet. I meant to say that. It's the radius of gyration derived from this equation, right? It's the moment of inertia is equal to the area multiplied by the square of the radius of gyration. And so the radius of gyration is some kind of a section property, just like moment of inertia and area. Now, it's always like this, when I was in the steel design class, and when I ask a question, what is the engineering meaning of moment of inertia? Generally, it's no surprise that nobody knows it. The engineering meaning, not moment of inertia is equal to AR square. Yeah, everybody knows that. But what is the engineering meaning? Why do we need to have this? You guys should know. I should have said that in the class, but yeah, it's been a long time, so it's gone somewhere to the universe. The moment of inertia is the property of the section that tells you how hard it is to rotate that section. The greater the moment of inertia means that that particular section is harder to rotate about that axis. So if you have Ix greater, very, very great number of Ix, it means that that section is very, very hard or difficult to rotate about the x-axis. That is the meaning of moment of inertia. And the meaning of the radius of gyration is that it tells you how well the mass of your section is distributed to fight against rotation. So the greater the R, it means that the mass of your section is far away from the centroid. and therefore your section becomes harder to rotate in that axis. Okay, to maybe this is better. Let's say if this is the axis, I have my section here. I want to rotate this section about this axis. It's very easy, right? Just like that. But if the axis stays the same, but now instead I have my section over here, and I want to rotate this about the axis, the same axis, it becomes harder, right? Because the axis is here, but now I have to rotate like this. So the farther away the mass from the axis, the better that it can withstand rotation. And this is the main reason why we use the shape such as this. Because now your mass is away from the axis of rotation, so it is harder to rotate. And the value of R will tell you the index of the mass that is away from the centroid. So the larger the R number, the more mass is away from the centroid. So the harder the section to rotate. Right? That's the engineering meaning. I know this because I used to teach statics. I have taught like 10 classes in the university. So yeah, it's in the mind. But it's beautiful when you know the meaning and you know what you're doing. And wow, we use this to try to approximate the strength of the column. Wow. Like that, right? Oops. Okay. So now you know. And Leonhard Euler, I don't think he was a civil engineer, but somehow he knew this. Must be a piece of cake for him, right? Because he created so many crazy series and equations and calculus and whatnot. So it's kind of, Euler, I got some free time, so let me approximate the strength of column for you guys so that you could use it in the future. And so we should thank Euler for that. Anyway, Leonhard Euler, nonetheless, was a mathematician. So his equation is a mathematical answer to this, which means it doesn't incorporate the real behavior of the column in the real world because he's not an engineer, right? So we cannot use that equation right away. Because even though this is correct, and the boss is coming in, can I have like a few more minutes? It shouldn't be so painful. This is theory, and it is correct. And it says that here, see, it's a stress, but this is not yet F critical. It's not yet a critical buckling stress. This is elastic buckling stress. At first, I thought E stood for Euler, but no, the E is elastic buckling stress. It's a theoretical buckling stress, which means that it's a theory. We cannot use it. We need to incorporate some application into it so that we can use this discovery to approximate the strength of the column. First of all, if you look at this equation, if L over R approaches 0, where does Fe go? Infinity, right? Can we have infinity stress? It's not infinity stone, right? It's a stress. So we cannot have that. In the real world, we have the material, and the material cannot have the stress approaches infinity. So we need to do something about it. And not that, and there's a few more things. And remember, this is the theory. We're going to use it, but we cannot use it right away. We need to do something about it. And that we will do after lunch, right, boss? So let's resume our session. I think I have spoken in the casual pace so that we're not going very quickly, and I don't know if we have enough time to finish everything, but let's just go with the same pace, okay? Now, it's been mentioned in the morning that this is the the theoretical graph or formula obtained under, say, the perfect scenario. Okay, but in the real world, we need to take into account a few more things so that we can have the real design formula that can help us approximate the compressive strength of the column. So the first thing is that, as I mentioned, we cannot have the stress close to infinity. It's impossible. In the real world, we use the material that is going to yield at one point. Okay, so that will happen in the region where we call the behavior inelastic. Now, before I go into more details, let us clear this first. You have the clear idea what the elastic means? Elastic means that when you apply the force and then you remove the force, it will go back to its original state. So that is elastic. And the relationship between the stress or the force and deformation is generally linear. Okay? And so if our structure behavior is in the elastic region, that would mean as soon as we unload the structure, everything should go back to normal. Now, when we face the word inelastic, of course, that's the opposite of elastic. So that means either we don't have the linear relationship between stress and strain, or when we unload the structure, it will not go back to its original shape. That means, in other words, there may be some permanent deformation. Okay? So when we have inelastic buckling, generally it means that your structure can take so much load that some permanent deformation may occur. So in the inelastic region, generally the structure can take more load. And in the inelastic region, when our compressive member or column carries the load into that behavior, we will have the problem with yielding, of course, because if we continue to pour more load onto the column, it's going to carry more and more and more and more, and therefore the stress in the cross section is going to keep increasing, correct? But no matter how much stress keeps increasing, it can never go beyond Fy. And that is the first limitation that we need to put on Euler's theoretical curve. Because if you go back here, you see that it goes forever, and the stress will reach infinity, which is not true. We need to cap that off. A second is the problem with what we call the residual stress. Residual comes from the word reside, which means to live in. Right? So the resident is a person who lives in the house, right? And residential area is the area that we can live in. So the residual stress is the stress that already lives in the structure. Now this stress in steel generally comes from the manufacturing process, because once you roll the section out of the hot roll procedure, the heat that remains in the structure will cause the structure to cool in different rate. And when the cooling down process is not the same, say between the end of the flange and the point where the flange is connected with the web, because it's not going to cool down at the same rate. So it's going to be bent, because this part want to cool down, but it cannot because it is attached to the web. And that restraint from the web and so on will cause the section to have stress before we even use it. That is why it is called the residual stress. The stress that is already there before we put the load on our structure. So the stress does not begin from zero. Okay? That is one thing that we need to put onto Euler's curve. So two things now. And the last thing, my advisor calls it out of straightness. Because when you manufacture the column, how can you be sure that your column is perfectly straight? With one tiny, crooked shape somewhere, it means that when you apply the axial force, it's going to cause more internal force in the structure because of the eccentricity, right? Because the force does not go straight to the centroid because the column is crooked. So we call that out of straightness because your column cannot be perfectly straight all the time. So three things we need to take into account and readjust Euler's buckling curve. Okay? And from that, we have to cap off this curve by Fy, of course. No matter how well you do, you can never have stress more than Fy, right? It's common sense. And from the test, they found out the effect of the residual stress and the out of straightness, and therefore from the original curve here, the dotted line, the design curve has been the curve that its value is reduced from the original one. Okay, and therefore we have this curve for our design, and from theory now it becomes a business of curve fitting. Okay, and this is the inelastic region. You see, where we have the very small slenderness ratio, or the column is pretty strong and thick. Okay, and if the column is strong and thick, it means that it can carry a lot of load. And when it can carry a lot of load, when the failure occurs, it is going to occur in the inelastic region, which means some permanent damage will occur to the column. But we can take a lot more load. In other words, if you look at this side, the column is so slender that when we apply not so much load, the column becomes unstable very quickly. So it becomes unstable very quickly, it goes off, we take the load off, it goes back to its original position. Because the buckling behavior in this region is elastic. It sounds good in one way because we don't have damage on our structure. But it also means that you have a very slender structure that cannot carry as much load as you would want. Okay? So this is, you can see the stress is coming down here because we have the slenderness ratio very, very big. The more it goes on, the less the stress that it can carry. Okay? And this is divided into the inelastic region and elastic region, and therefore we must have some kind of limit here to separate the two sets of behavior out of each other. And the formulas are in the next slide. Okay, the limit here is 4.71 square root e over Fy. Again, this is looks newer than the one that you used to have with ASD 89. It's pretty convenient again because e and Fy are both in the square root and makes this term unitless. Okay, and if you use the SS 400 or SM 400 steel, Fy is 2,500 kilogram per square centimeter. This limit is about, I think, 132. Okay, it's a basic number. If you use SM 520, it's gonna be down dramatically because the stronger the material you have, the lower the buckling limit you're gonna have, because when you have a stronger material, it can take more. So that means it should be limited to have a buckling earlier because of a stronger material. It makes sense, right? Now, in the inelastic region, the critical buckling stress can be approximated by this formula. This is the F critical, the stress that should occur when the buckling of the column occurs. Okay? Notice that this formula is a function of elastic buckling load. That means you're going to have to calculate this elastic buckling load, which is the Euler discovery. When you have this, you plug it in here. And then there is this formula. Now, how can we choose between the two? We choose based on the slenderness ratio here. If you have the slenderness ratio of the column less than this value, it means that your column will have the inelastic behavior, and therefore the critical buckling stress can be approximated by using this formula. If your column is so slender that it is beyond this limit, it is going to have the elastic behavior, and the critical buckling stress can be approximated by using this formula. Okay? If we can see the behavior, this is just merely a calculation, nothing more. Okay? And notice that this is the elastic buckling load, right? It comes into some kind of formula when you are in the inelastic region. But for the elastic region, it's just this multiplied by a constant. See that? And in the elastic region, the only problem that we have to deal with is out of straightness, or the problem with the fact that your column may not be perfectly straight. In the inelastic region, you have to account for yielding, residual stress, and out of straightness. So when you look into this formula, you can see that to make sure that if your column is not straight, it's still okay. We reduce the strength from elastic buckling strength by 12.3%, according to the number. Simple as that. So now, if you know the slenderness ratio of your column, you can approximate the critical buckling stress, and when you have this, you now have the nominal strength of your column or compressive member. That's simple. Okay? This is pretty much the same idea as the ASD 89 as well, but the calculation that we will use in approximation is different. Okay? I think I have that in the end of the slide, so you can just wait and see for yourself. That is the idea. This is what you may see if you look at the specification, and rather not very friendly, right? If you look at it, oh, what is this? But now, if you have this picture in mind, you should know how the formulas work, and that's it. It's the same formulas, but this is put into graph, and that's in the spec. One more thing that you need to know is that I believe that most of you here should have an idea about the unbraced length and the slenderness ratio, right? You or you not? Let's talk about that for a minute, okay? Now, this is not the length of the column, you know? This is the unbraced length, the length between brace points, the length where the column is free to move. So, for example, what's this? Okay. For example, if you have a column that long, let's put some support on it, and I prevent the movement at that point. This becomes the unbraced length, right? If I somehow find a way to prevent this point from moving in this direction and that direction at the same time, that means my column will be free to move like this. And the strength of the column will be based on this unbraced length, this unbraced length, and this unbraced length. The length of the column may not be the same as the unbraced length. So we need to understand this. And when we know that our problem with member under compression is buckling, which means it's going to go sideways, so if we can find a way to control the movement, it means we can prevent a buckling from happening. Or let's say if I put the concrete around this column entirely so that the column cannot move at all. It means it cannot buckle, right? So the unbraced length becomes 0 if I cast concrete around it, because it cannot move. So buckling cannot occur. So that in that case, my F critical will become Fy, right? But in this case, if I don't do anything, it is free to move like this. That becomes my unbraced length. And therefore, the F critical will depend on that, because F critical is a function of L over R and Fy. Of course, I can write that. So now that we know compression will cause buckling, it will cause columns to move sideways. So if you can prevent that movement, you can a bit control the critical buckling stress of the column. And of course, now we don't have the column as a line like this. And you should know that when we have a column that is a shape of an edge like that, now we have the, let's say, radius of gyration and moment of inertia different for two axes. So when you have a case like this, you are going to need to check the slenderness ratio of both axes, right? That is why we need to check and find the maximum L over, the maximum L over Rx and L over Ry. The maximum value will mean that in that particular axis it is more slender, and it is going to go buckle in that axis first. And that becomes the governing strength of your column. So in general, if we have the x-axis and the y-axis like this, and I don't do anything, the y is weaker, right? So it's going to buckle in that axis, this axis first. Because Ry is related to Iy. And Iy is generally smaller than Ix. So it's going to buckle in this axis first. Correct?